Thanks again to the organizers. It's been a good conference, really, really well organized. So this paper here, Sarah Lenardi actually contacted me a year ago and said, you know, we're doing this like 50th anniversary decentralization conference. Do you have any work that's related to sort of the work that's been the foundation of, or the history of this conference? Anything related to what John Ledyard's been working on? And I said, well, I have a conjecture. I don't have a paper. I have a conjecture. So I've been scrambling to put together to see if this project to see if the conjecture is true or not. So it turns out the conjecture was true. So let me show you the idea here. So we're going to be studying public goods economies and the problem of public goods. In my mind, the Groves-Ledyard mechanism, which I'll show you, I think is still the best solution out there in theory for solving the public goods problem. It has only one Achilles heel, which is that individual rationality violations can still occur, right? So sometimes running the mechanism can actually make participants worse off than if you just left them at the initial endowment, right? And so there's a question that's been running in the literature of, can we fix this IR failure with the Groves-Ledyard mechanism by somehow picking a different mechanism or changing it? And recent results have shown that you cannot get rid of, or you cannot fix IR without giving up some other nice property of the mechanism, such as its dynamic stability properties or its simplicity properties, right? So the recent literature on this stuff has worked on giving up simplicity and designing more complicated mechanisms that are going to guarantee individual rationality, okay? What I wanted to do is take this in a different direction and say, well, let's not give up on any of the other properties. So we know that we're going to have some IR violations. The question is, can we at least make those IR violations less frequent or less severe? Okay, so we're still going to have IR violations in this mechanism if we can find such a mechanism, but can it be better than the Groves-Ledyard in terms of frequency or severity of those violations? Right, and the result is, yes, we were able to find a mechanism that in some sense does have fewer IR violations than the Groves-Ledyard mechanism. I'm not going to claim that this is a super awesome result because it's very much a limiting result as some parameters go to infinity. It requires some specific assumptions about uncertainty about the environment and so on and so forth. So I'll say it can be done. I'm not going to claim that this dominates the Groves-Ledyard mechanism or anything else that's already out there. Okay. All right, so let me give you the setting. We're going to have some agents, at least 3 agents, a finite number. There's a public good, which is denoted Y, which is a real number. And there's one private good, XI, for each individual. Everyone has an endowment, but we're going to normalize endowments to 0. And everyone has to pay some tax to fund the public good. We're going to assume a constant marginal cost of the public good, which is kappa. And every agent has a utility function over the allocations. It's going to be depending on some type, theta I. And we're going to assume for this talk quasi-linear preferences. There's a whole host of reasons why we want to make this assumption. Dynamic stability, for one, is impossible without something like quasi-linearity. So we're going to assume that preferences come from some set script V, which is a set of nice, continuously differentiable concave value functions. All right, so that's our environment, pretty classical. And if we go to Samuelson, 1954, what's the condition for Pareto optimality? In an economy like this, it's that the sum of the marginal benefits equals the marginal cost. So that's the Samuelson condition. And you need budget balance, which is that the sum of the transfers equals the total cost of the public good. All right, and the IR constraint is that the allocations utility for every agent be greater than their utility at the initial endowment where there was no public good. All right. One way to guarantee IR is satisfied is to choose a Lindahl allocation. So a Lindahl allocation is one where everyone's tax is just their marginal utility at the Pareto optimum times the level of the public good. So it's like they pay a personal price that's equal to their marginal utility. So it's marginal utility pricing. And under a concavity assumption on V, it's easy to see that this allocation here is not only Pareto optimal and budget balanced, but it is also individually rational. Right? So the Lindahl allocation is kind of like a gold standard allocation that satisfies all the things you'd want it to satisfy. All right, now how can we implement Lindahl allocations or other desirable allocations? We're going to use a mechanism, right? It's decentralization conference. So a mechanism is a message space, right? Agent's going to submit messages M, and there's going to be an outcome function G that takes those messages and spits out an allocation, right? A public good level and a tax for each person. All right, I'm going to do a little bit of history lesson just to build up the Groves-Ledyard mechanism, where it comes from. So where it comes from is the VCG mechanism, which I know you all know, but the VCG mechanism starts off with fixed cost shares. Everyone is responsible for some percentage of the cost of the good. You can think of this as like 1 on n. And it's a direct mechanism, so you announce your value function. Let's let v hat be your announced value if your true value is v. So v hat is the vector of announcements. The VCG is going to be designed to satisfy the Samuelson condition. So whatever the announced valuations are, we're going to pick a level of public good such that the sum of the announced marginal benefits equals the marginal cost. And this is the trick that makes it work. The tax that we charge you is your share of the cost, but then we pay you the sum of everyone else's announced value. This is going to align preferences so that people will report truthfully. And then we charge you a Clark tax, which is the maximum that the sum of everyone else's value would have been if you hadn't been part of the economy. Okay, and we know that truth telling here is a dominant strategy in the VCG mechanism, right? So that's the good thing about it. It's a demand revealing process. All right, there are two big problems with the VCG mechanism, or more than two, but one is that budget balance can fail. So this Clark tax will generally collect more money than it costs to fund the public good. And the other problem is that IR can fail, right? That there can be agents who are made worse off by participating in the VCG mechanism. So to sort of summarize the properties of a VCG mechanism, it's equilibriums and dominant strategies. It does satisfy the Samuelson condition, but it's not budget balanced. It's not individually rational. It does have a complicated message space. The message space is the space of all value functions, admissible value functions. It does have the nice property that it's stable, the equilibrium is stable, but that's because it's a dominant strategy. Okay. All right, so that's the VCG mechanism. The first thing I'm going to talk about is the budget balance problem. So it's generally not budget balanced, but Groves and Loeb and Lafont and Maskin showed that if preferences happen to be quadratic, then the budget will actually balance. Okay. And so what do I mean? We mean that if everybody's preferences v can be written as a quadratic function with this, this intercept term and this slope term, then the budget will be balanced. So here, everybody has a common gamma term, and then each person has their own individual type theta I. That's what differentiates the different players, the different possible utility functions. All right, and then let's let VQ be the set of all such quadratic valuation functions. And the idea is if everybody has quadratic preferences in this family, then it'll be budget balanced. And really to announce your preferences, all you need to do is announce your theta I, which is just a single number. So it also becomes sort of informationally simple in a different way, which is that the message space is just a single number. Okay. So we just need people to announce a single number, which is this theta I parameter. Right, so the VCG, when we have quadratic preferences, gains the advantage of budget balance. Okay. But there's the problem. Of course, we don't think that people really have quadratic preferences. So here's where the genius of the Groves-Ledyard mechanism comes. So the idea that behind the Groves-Ledyard mechanism is we know that people don't actually have quadratic preferences, but what if we force them to pretend they do, right? So we allow them to have any quasi-linear preference, but we require them to announce a quadratic preference, right? So the truth will be some VI, which is in arbitrary V, but they have to announce V hat in the space of quadratic preferences, right? Now, if your true preference is quadratic, then it'll be a dominant strategy to tell the truth. But what they show is that if your true preference is not quadratic, at least your best response will be to announce some quadratic preference that has the same marginal utility as your true preference. Okay, so even though you won't announce your true whole preference, you will announce your marginal utility truthfully. Okay, so you'll announce a message that at least gives the right marginal utility at the equilibrium allocation. But it's no longer going to be a dominant strategy. It's just going to be a best response. And so in Nash equilibrium, everybody's best responding. So in Nash equilibrium, everyone will be announcing their marginal utilities truthfully. But the mechanism takes the sum of marginal utilities equal to kappa. And so the nice thing about it is that the resulting outcome actually will satisfy the Samuelson condition. Okay, so you'll get the Pareto efficient level of the public good in equilibrium, in Nash equilibrium. And everybody's announcing these quadratic preferences, so the taxes add up to the cost of the good. So it's also budget balanced. So the cool thing about this is you force people to announce quadratic preferences, they end up in Nash equilibrium with a public good level that is Pareto optimal and budget balanced. And remember, for quadratic preferences, they don't need to announce the whole function. They can just announce that one theta I, right? So the message space can just be the single numbers. They announce theta I will be their message. And then the level of the public good, it turns out, when you simplify everything, is just the sum of the messages. Okay? So we can interpret these messages as like how much you want to add to the public good. And what is the tax that each person has to pay? It's their share of the cost plus this quadratic penalty term, right? Excuse me. Right, so you have to pay your share of the cost of the good, which is a linear term. Plus you have to pay this quadratic penalty, where this is the difference between your message and the average of everybody else's message. And then you get a bonus back for variance in the other's messages, right? So you get a bonus back if other people report messages with high variance, okay? So that's just how the math works out when you do this quadratic announcement game. So to summarize, the Groves-Ledyard mechanism, it moves from dominant strategy to Nash equilibrium, so that's a bit of a weakness. But it's, we've got Samuelson condition, we've got budget balance, we've got simple message space, and the only thing that's failing is IR. Okay. Now, what about stability? I haven't talked about that. So first, I know I'm going really fast, but let me motivate why stability matters in public goods games in particular. Okay. So in public goods games, there tends to be a lot of strategic substitutes. Right? So if we take, for example, a proportional tax game, this game generally doesn't have an equilibrium. The reason is each player, if the tax function is just proportional to the total level of the public good, each player will have a different ideal level of public good that they'd want to produce. All right, so player one would want like 10 units of public good, and player two would want 20 units of public good. And that's going to generate massive instability in the messages. So think about if the two players submit messages 5 and 5, that adds up to 10. Player two is not going to like that. He's going to add 10 to his message to move it up to 20. But then player one's not going to like that. She's going to subtract 10 from hers to push it back down to 10. But then player two is going to add 10 to his. Then player one's going to subtract 10 more. Player two is going to add 10 more. And they're going to just push away from each other, okay, blowing up towards positive and negative infinity. So this is a systematic problem in public goods settings, that they have this sort of strategic substitutes. And so you get this massive instability. The way the Groves-Ledyard mechanism prevents this from blowing up is that quadratic penalty term, right? So remember, there was this penalty for announcing a message that's different from the average of everyone else. Well, if we're announcing the same thing, that penalty is 0. But as we start moving away from each other, that penalty blows up, and it's quadratic, so it really blows up. Okay, so we're not going to keep diverging away from each other because it just gets too costly. Right, so this gamma term is the weight that we put on that quadratic penalty. If that gamma term is large enough, then this cost to diverging is going to discipline behavior and keep the equilibrium, it's going to generate an equilibrium that's, that's interior, so they won't blow up. Okay, and it'll be dynamically stable, and that they'll converge to that equilibrium. All right, and lab evidence confirms that the stability property is in fact important. If you put these mechanisms in the lab, when it's dynamically stable, players will converge to the equilibrium and you'll get good outcomes. If it's not dynamically stable, the players will bounce all around and they'll get bad outcomes. Okay, so yes, it's dynamically stable as long as the gamma term is large enough. Okay. And that also means that the Nash assumption is maybe less worrisome, because as long as the play is repeated and players are somewhat myopically best responding or dynamically adaptively adjusting, they're going to converge to that Nash equilibrium. All right, so the only problem, like I said, the only problem remaining is the IR problem, right? There are some economies where people will be hurt by playing this mechanism. All right, so what can we do about the IR problem? Hurwitz has this paper that says, if you want to implement Pareto optimal public goods levels and satisfy IR, you have to implement Lindahl allocations. There's no other choice. He has a continuity assumption in there too, but you have to implement Lindahl. All right, so Mark Walker comes along in 1981, a few years later, and he comes up with a mechanism that does implement Lindahl. Okay, it's kind of a funny mechanism where everyone submits a message. The public good is the sum of the messages, and then the price that you pay is your share of the cost. That should be times kappa. Sorry, your share of the cost plus the message of the guy to your left minus the message of the guy to your right. Okay, so everyone's in a circle, and the messages of your neighbors actually determine the price per unit of public good that you pay. Okay? And incredibly, this works. The Nash equilibrium, if you solve the system of equations, the Nash equilibrium gives a Pareto-optimal public good level and Lindahl taxes, so it's Pareto-optimal and it's individually rational. Right. Unfortunately, it's not going to be dynamically stable. In fact, I have a paper with Laurent Matheve where we show that if you have a mechanism with a one-dimensional message space and you want to implement Lindahl allocations, it has to have this form where your tax is some function of other people's messages times y plus nothing else. So that quadratic penalty term in the Groves-Ledyard that disciplined behavior and gave stability, that can't exist if you're implementing Lindahl allocations. So there's this fundamental tension that if you want PO and IR and a simple message space, then you have to want a Lindahl mechanism. But if you want a Lindahl mechanism, you can't get stability. So there's an impossibility result. You can't have everything. And I already kind of said this, but stability really matters. So in the lab, if you compare Groves-Ledyard to Walker, here's the level of public good over time. It's pretty stable with Groves-Ledyard, and it really bounces around with Walker. Efficiency levels converge pretty close to 1 for Groves-Ledyard, and they bounce all over the place for Walker. Right? So stability matters a lot. All right, so going back to our chart, Walker is Nash equilibrium, has all these nice properties. It satisfies IR, but it gives up stability. And you just saw from the data that giving up stability is a pretty bad thing. Okay, and so we know that there cannot exist any mechanism that satisfies all the things that we want. So you have to give up something. All right, so what has the literature done so far? They've focused on adding complexity. Okay, and what do I mean by complexity? The papers in the literature have gone to a two-dimensional message space. So instead of announcing a single number, now the agents are going to be announcing two numbers. And it turns out you can construct Lindahl mechanisms with a two-dimensional message space, and there are a bunch that have been done, and you can make these dynamically stable under certain parameter restrictions. Okay, and it's even been tested in the lab. There's a paper by Matt Van Essen and Lazzaди and Mark Walker that show that at least like this Kim mechanism here performs pretty well. It's dynamically stable. Okay, the subjects actually converge. Just for your curiosity, there's what the Kim mechanism looks like. The players have to announce two numbers. We're able to get this quadratic term in the second dimension. So we get stability sort of in the second dimension that people are announcing. And then that's going to give us the dynamic stability, but then we still have sort of this Mark Walker stuff going on that gives us Lindahl. Okay. Now, it turns out the Kim mechanism is not budget balanced out of equilibrium. So when they're converging, before they get to equilibrium, we're not balancing the budget, which is a problem. Okay, Laurent and I found a way to balance the budget by adding a whole bunch of extra terms to this thing. It turns out that just adds a ton more complexity. So if you want budget balance out of equilibrium, you have to blow up the complexity again. Okay, so it's not a really satisfactory solution to the problem. All right, so yeah, you can get IR and stability, but at the cost of the message space has to become more complicated. The mechanisms become more complicated. All right, so that's the trade-off that's been made so far in the literature. All right, now finally, let me get to what we're doing. Right, so past work is insisting on IR, which means Lindahl, and giving up on simplicity, so two-dimensional message spaces. Okay, like I said in the beginning, the idea here is let's go back to simple mechanisms, meaning one-dimensional message spaces. I'm going to insist on dynamic stability because I think that's important, and budget balance, of course, and simplicity. I'm going to give up, though, on IR, like Groves-Ledyard does, but I'm going to try to reduce those IR violations. All right, so can we alter the Groves-Ledyard mechanism to minimize the IR violations that it generates? All right, so our goal would look something like this. It's going to look just like the Groves-Ledyard mechanism, but the IR violations are going to be less severe. All right, we've tried lots and lots of things. Excuse me. It turns out that what works for us is pretty dumb. You just take the Walker mechanism and the Groves-Ledyard mechanism and you blend them together, right? It's not super genius at all. So you just put weight lambda on the Walker penalty or the Walker price term, and then the Groves-Ledyard still has its weight gamma. Okay, so our new mechanism is literally just this: lambda times the Walker mechanism, gamma times the Groves-Ledyard mechanism. So we'll just call it the Walker Groves-Ledyard mechanism. Okay. Now, nice thing about it is, as you take the parameters to 0, you get the original mechanisms back. So this sort of nests the original mechanisms. All right, so stability is important. So under what conditions do you get stability? And the answer is, it's very similar to Groves-Ledyard. If gamma is large, then it's going to be stable, but we have an extra requirement, which is that lambda can't get too large with it. So you can have gamma and lambda growing, but lambda needs to grow somewhat slower than gamma. In particular, it can converge to a finite number. The ratio can converge to a finite number, but it has to be less than 1 on n. So you can't let the Walker term get too big. The Groves-Ledyard component needs to sort of dominate the Walker component as the parameters get big. Okay. Obviously, for a given economy, lambda doesn't have to go all the way to infinity. You just need sort of large enough gamma. You need a large enough gamma. But for any arbitrary economy, it might have to be pretty big. All right, so our objective is to compare the equilibrium utility between the Walker Groves-Ledyard mechanism and the original Groves-Ledyard mechanism, okay? And we're gonna only be focusing on these stable cases where gamma is big and this ratio stays below 1 on n, okay? And at the beginning I said our result is a sort of a limiting result. This is what I mean. So we're only gonna be looking at how these mechanisms perform for large gamma and lambda over gamma bounded by 1 on n. All right, so the first result is that for any given economy, unfortunately, it can go either way. Some cases the WGL wins, and some cases the GL wins, okay? So it's not like one's uniformly better than the other. So what we need to think of instead is something like in expectation is one better than the other. So we're gonna switch gears to that and think about a planner who has uncertainty about which economy exists, right? And here's how we're going to model that. So the planner's uncertainty about the economy is, first, the value functions get drawn at random. So n value functions get pulled out of a hat. And then second, those value functions get handed out to the players in some random way, right? So the players have names 1 through n, and these n value functions get assigned to them randomly. Okay, and let's assume uniformly. So everybody's equally likely to get one of the value functions, right? And now we're going to see if the IR violations are reduced in expectation with this sort of uncertainty about what economy is going to be drawn. All right, now what we can show is that if you want to reduce IR violations, what you need to focus on is improving the utility for what we call the low types, right? So this term here is your marginal benefit, your net marginal benefit at the Pareto optimal y. Okay, this is your marginal benefit minus your marginal cost at the Pareto optimum. Okay, those types are more likely to have IR violations. Okay, now the sum of marginal benefits equals the marginal cost. So these terms sum up to 0. So there's going to be some people who are low types, and there's going to be some people who are high types. So every economy does have some low types in it, at least one, they have to. Okay. Now the high types are less likely to have the IR violations. So we're going to focus on low types. All right, so here's the statement of our result. Suppose that the vector has been drawn. So any vector of value functions has been drawn. Now fix a person I who got assigned a low type. Okay. Now leave the other assignments of values to the remaining values unknown. And note that those are more likely to be high types because one low type's already been assigned. Let gamma be large and let this ratio be bounded by 1 on n for stability. Then the low type, this low type I, their equilibrium utility is higher in expectation under the WGL than under the GL. Okay, so it does work in expectation. The low types are made better off under the new mechanism, the WGL mechanism, than under the original mechanism. All right, so we can reduce IR violations on average compared to Groves-Ledyard. Right? And since this is true for every draw of n value functions, then it's also true sort of ex ante before they're drawn, of course. Right. All right, now there's a crazy thing about this result. It's hypersensitive to a lot of things. One funny thing, yeah. Oh, thank you. I won't even need 5. Okay, there's one crazy thing about this. That our mechanism, the penalty function, is that the price depends on the player to your left minus the player to your right. What if we switched it to I plus 2 minus I plus 1? So 2 to your right minus 1 to your right. It seems like that shouldn't matter, right? So this low type, every other person is sort of ex ante identical. Everyone else could equally likely be a high type or a low type and have any of the other valuation functions that remain. So you wouldn't think that the identities of the two people that determine your price would matter at this sort of ex ante stage. It turns out it does. In fact, this mechanism works. It reduces IR violations. This mechanism doesn't always reduce IR violations. It does for n equals 3 and 4, or n equals 3, but it does not for 4, 5, and 6. It does for 7. It's very bizarre. And the reason is that changing the identities of the people who affect you also ends up changing the weight you get in equilibrium on your own value in a very sensitive way that has to do with matrix inverses and so on. So it's like if you change the identities of who you're matched with, it changes how much your own value determines your own equilibrium payoff, and that messes up things in a way that's hard to explain. Okay. All right, so that's it. That's all I'm really going to say. So I'll sort of, in summarizing, is this a good result or not? I'm sort of torn. So yeah, we were able to get a result. It is possible to reduce IR violations by blending in this Walker mechanism in the right way and looking at sort of this ex ante perspective where we don't know the assignment of values to players yet, and we just look at the low type and see if they're improved or not. So we were able to do it. I'm not super excited by the result because it's very sensitive. First of all, this is all, as these parameters are very large for stability. If these are finite, then I have no clue if this result is still true. It probably depends on the economy. And like I said, you have to get the permutation of the opponents right. It has to be guy to your left minus guy to your right. Nothing else works always that we know of. And it's true the mechanism is slightly more complicated in that the Groves-Ledyard doesn't have your payment depend specifically on one other guy, like the guy to your left or the guy to your right. This mechanism does have that sort of weird cyclic feature that I think a lot of people find undesirable, and I kind of agree. Okay. So yeah, the WGL exists. It has some expected benefits. There's in some sense kind of knife edge because it requires these large parameter values and specific setting of these permutations and so on. But it was able to be done, I guess, is the conclusion. So with that, I'll stop.